Hello, and welcome to another edition of DDI's Productivity Webcast Series. I'll be your host, Joseph Richter, and today we're going to talk about design studies, the automation of design intent. Design studies is the function of taking a model and telling SOLIDWORKS to flex or change a few dimensions, recalculate the result until it meets a predetermined goal. In order for this to work properly, your model requires good, clean design intent. That is, you built it with change in mind. You know how the part's going to change when you flex the dimensions. And part of that design intent would be what I call model preparation. And with that are things like renaming features and dimensions so that when I go to assign equations to dial in my design intent, equations are relationships between your dimensions, you'll understand what the equation editor is actually doing based on the name of those dimensions. After you have your model prepared, there's one more requirement for design studies, and that is sensors. Sensors are like timers or watchdogs that will keep track of your model based on certain criteria. The design studies can read this criteria and either pass or fail your results based upon those sensors. Once our model is prepared and we have our sensors ready to go, we then set up the design study. I'll walk you through how to set up a design study, and I actually have a couple of case studies here. One is a design study of a water bottle, and this is straight out of the help file with minor modifications. Then I'll take you through the design study of this fish tank that you see here. And then I'll show you how to take your design study and get a report out of it. Then we'll talk about some in-context modeling strategies, that is multi-body part design versus in-context assembly design. We'll talk about the pros and cons and what I recommend. Then I'll briefly show an example of design studies being used in simulation, and then we'll close out on best practices. So to prepare your model for a design study, aside from design intent, which as your model changes and behaves in a predictable manner, there are a few other things that you can do that will make your model easier to use. One of the things that you can do is rename your features. To rename your features, either slow double click or selecting the feature and click F2 on the keyboard, and then you can type in a new name. Likewise, you may want to rename some of your dimensions. When you select a dimension in the left-hand side there for the dimension properties, under primary value, you will find the name of the dimension. To rename it, simply swipe over this value and type in a new name. Here in my example, I have height at extrude 1. Now, if I had renamed the feature of extrude 1, then I would know which height I'm talking about. Then, to help ensure clean design intent, you can use equations. Equations are a way of establishing a relationship between dimensions that may be otherwise difficult to achieve through modeling techniques. And provided you've renamed your dimensions, writing an equation will be less cryptic because you'll know exactly what the equation editor is trying to do. And with that, let's go into SOLIDWORKS to take a look at this. So to rename a feature, you slow double click or hit F2 on the keyboard, then give it the new name. You can also rename sketches. And one advantage to renaming your features is you can search the tree by the names. In order to rename a dimension, you can double click on a feature to expose the dimensions, click on a given dimension, and then rename the dimension. Next time I take a look at that dimension, it's going to have, in this case, diameter at renamed sketch. So I know what the name of the dimension is and where it's located. So it's located at the renamed sketch. To add an equation, I'm going to show my dimensions again. Find the dimension that I want to drive with the equation. So this dimension here, which I've named height. Okay, I'll use the drop down here and add an equation. And I'm going to say that that height shall be equal to the diameter divided by 2. Now when my diameter changes, it'll adjust the height. So to test that, I just double click on my feature, find my dimension, change my dimension, hit rebuild, and watch it update. To show that again, maybe I'll take this other dimension over here. So take this 20, which is named hole. And I could say that that should be equal to my diameter divided by 3. So now my diameter is driving two other dimensions in my model. So when I make a change and hit rebuild, the hole and the height are getting updated. So again, this allows me to add relationships between my dimensions that may otherwise be difficult to capture through modeling techniques. And if I ever need to get back into my equations, you'll notice the equations folder in the tree. You can right click there to edit your equations, or double click to find your dimensions, double click on a dimension with an equation, use the drop down to edit the equation. And with that, let's get back into the slideshow. When I make a feature that breaks the model, SOLIDWORKS is not bashful. It throws up a nice error flag and tells me that whatever I'm doing is wrong. Well, that's great for SOLIDWORKS, but what about me, the designer? I know that I need a specific dimension to be within a specific range. Wouldn't it be nice if SOLIDWORKS would let me know if my dimension was not in that range? Well, that scenario is exactly what sensors are for. Sensors allow you to build in design rule checks, so when a specific design requirement is violated or exceeded, it'll error out and then you'll know about it. So now I can specify a given dimension, and granted there are other sensor types, but dimension is the one I'm using here. SOLIDWORKS will inform me when my dimension does not meet the requirement that I've specified. Some of the other sensor types are mass properties. It'll track things like mass, volume, or surface area. Dimension, as I'm mentioning here, will monitor the dimension that you pick. We also have sensors for simulation data that allow you to define locations for measuring result quantities in simulations. Now, depending on the SOLIDWORKS product that you have will determine the type of sensors that you have available to you. So for SOLIDWORKS Standard and SOLIDWORKS Professional customers, you're going to have mass property sensors and dimension sensors. However, it isn't until you have the SOLIDWORKS Premium where you have SOLIDWORKS Simulation will you actually get simulation data sensors. And for the purposes of this webcast, as long as you have SOLIDWORKS Standard, then you can do everything that I'm going to demonstrate, with the exception of the last item that I'm just going to show a design study having been used in a simulation to test a part. And with that, let's take a look at creating a sensor. To add a sensor to your model, you'll notice the sensor folder in your tree. If this folder is not present, you can right-click in the tree and go to Hide Show Tree Items. And then from here, Sensors, you want to set that to Show. Once that folder is there, you just right-click on the sensor folder to add a sensor. And as mentioned, we have mass properties or dimension sensors. If I was going to do a mass property sensor, I could have it watch the mass of this part. And then when I hit the plus sign, I can see the mass is being monitored. So when I change a dimension, my part gets updated, and so too does the mass. Now, if I want to make a dimensional sensor, I need to first show my dimensions. So to do this, right-click on your annotation folder, show the feature dimensions, and then add your sensor. And then, provided your graphics card cooperates, I want to choose a dimension type of sensor, and then find the dimension. And maybe I want SOLIDWORKS to alert me when this dimension is greater than 100. So now, if this dimension goes over 100, SOLIDWORKS will tell me. Now it says the following sensors have triggered the alert. Dimension is greater than 100. So now every time I rebuild, it's going to warn me that my dimension is larger than it's supposed to be. So to correct that, I obviously need to drop it below. And again, I can see my sensors from the feature tree. And with that, let's get back over to the slideshow. In order to create a design study, use the Insert pull-down, Design Studies, and Add. Or, if you go to the Evaluate toolbar, you will have a Design Study icon, and from there you can add. You will then be presented with this interface, and the first requirement here are variables. You'll need to define variables with model parameters. For example, I'll be using dimensions. And when I set dimensions, I have three different options. I can use a range for my dimensions. That is, I can set my dimension to be between 8 and 16 inches. Or I can specify a range with steps or intervals to check. For example, if I want to go between 8 and 16 inches, but check every 4-inch increments, so that means it'll check 8, 12, and then 16. Or I could specify discrete values for my dimensions. In this case, 8, 12, and 16. They are discrete in the fact that I typed them in. It just happens to be coincident that it matches my range with step values. Then you can define a constraint or multiple constraints using sensors. Constraints allow you to have criteria for the study to track, and it can either pass or fail based on that criteria. This criteria can give a range for that criteria to meet. And finally, you can specify a goal. A goal differs from constraints in the fact that a goal means this is what I'm trying to do. SOLIDWORKS, can you do it? Constraints, on the other hand, is more like a monitoring, issuing you a pass-fail based on your requirements, whereas a goal, it will either reach the goal, come really close, or fail altogether. Having a goal basically allows you to optimize your design. Keep in mind that I'm advocating that you use design studies to hit your preliminary design point. I would not expect, nor should you, that SOLIDWORKS design studies will hit your final design point right away. It will still require you to dial in, massage, or otherwise change variables to meet the final design requirement. Design studies is simply a quicker way to get to the preliminary design point so you can spend more of your time refining your design. Finally, there are options for your design study that include things like the quality of the study and the results folder location. Now, design study quality really is when you use simulation, your simulation will take a while to run, and if you have 45 iterations of your model to run, and let's say that study takes 2 minutes, that'll be a full 90 minutes that SOLIDWORKS will sit there and crunch that. Well, if you have this set to low quality, then SOLIDWORKS will go through and it'll pick iterations to run, and then it'll interpolate or extract the rest based on a trend. After it presents you with the data, you'll then be able to go through, and the items that it did not actually calculate, you can go through and have it run those iterations to find out if the trend that it predicted was accurate or not. And as far as the results folder location, when it is running those simulation studies, it will, of course, generate a bunch of results. So this allows me to point to where I want SOLIDWORKS to put those files. The first design study that I have to share with you is the water bottle. Again, this one's straight out of the help file with a few modifications. And to set this model up, our variables will be the following. Length, that's a range with step between 75 and 150 at a step of 25. The height, the H dimension here, I want to use discrete values, that is specific values, of 30, 55, and 80. And finally, the diameter, I want to set a range of between 15 and 30 millimeters. My constraint will be a sensor watching the volume of the water, and I want that water to be between 100,000 millimeters cubed and 110,000 millimeters cubed. And my goal is I want to have the minimum mass for this bottle. With that, let's go into SOLIDWORKS to take a look. So for the water bottle, I'm going to add a design study. Again, from the Evaluate toolbar, I can add a design study, or from the Insert pull down, Design Study, Add. Now, in order to add some variables, from the drop down here, I'll add parameters. And you'll note that I already have my dimensions showing. That makes it easier for me to access these. And the first parameter that I'm going to assign is this dimension here. And I'm going to call that the length. Next, I'll add the height, which is this dimension here. Then finally, I'll add the diameter, this dimension here. Once I've done that, I can exit out of the parameters box. And then down here for my variables, I can use the drop down to add these variables. And on the length, I want to use a range with step. I want my minimum to be 75 and my maximum to be 150. And I want a step of 25. For the diameter, I want to go a range from, let's say, 15 to 30. And then for the height, I'm going to go with discrete values, that is specific values of 30, 55, and 80. For my constraints, I'm going to add a sensor, and I want to watch the volume of the water. So I'm going to do select other here and look for that water volume there. And I want to track the water volume to be between 100,000 and 110,000 cubic millimeters. And my goal is to have, I'm going to track the mass of the bottle. So I can see the study here I've set up telling SOLIDWORKS which dimensions it's allowed to flex. So it can flex this dimension between 75 and 150 using steps of 25. It can then flex the diameter between a range of 15 and 30, and my height dimension between 30, 55, and 80 specific values. My constraints is I'm looking for the volume for the water to be within this range, and my end-all goal for this is to minimize the mass of the bottle. Now, because I'm using things like a range on my dimension and I'm using a goal, it requires that I use optimization. If I uncheck this, SOLIDWORKS warns me that since I'm using a range, I must use optimization. If I don't want to optimize and I just want to check, I could set from range to range with step or discrete values. Then I could disable optimization. But I just want to point that out. And likewise, if I try to delete my goal here, then I could not run it until I specify a goal. Again, because I'm trying to optimize, it requires a goal. So again, I'll do a mass sensor for the bottle. Once all those items are in there, I can specify run. And SOLIDWORKS is going to go through and flex all those dimensions for 15 different iterations. And if I click on these, I can see each version or iteration that SOLIDWORKS tested. Now the red results here failed because the volume was not within the range that I specified. Okay, the one that's gray here met my volume requirement, but it's not the lightest version. My optimal study here says, okay, this meets your volume requirement, but it meets the goal of being the lightest bottle that happens to capture the correct volume. Now, there's one thing I want to point out here, and that is this is not configurations. Even though I can click on each iteration and see the model update, okay, that's visual feedback of the items that it changed and tested for us. Okay, so this is separate from configs. I only have one configuration, and whatever study I leave it on last is going to be that model's state. Okay, so you want to watch that. If you do have design studies and you click on a given result, it's going to modify all your dimensions to that result and those variables from that study. Another thing I want to point out here about your design studies, variable view is the one that I was using. I would also point out the table view here. This allows me to see all of the scenarios. And if I wanted to, I could selectively uncheck the scenarios I don't want it to run. And you'll see that it went from 12 scenarios down to 9. Likewise, I could type and change some of these. So I could really customize this to do exactly what I want it to through the table view. The variable view is much quicker because I'm allowing SOLIDWORKS to do all the work for me. And the options for your design studies are found here. High quality, which is what I'm doing here, that's going to run through and do each scenario. If I did faster results, that's draft quality, if you will. That will pick and choose which iterations to run. Now, since all I'm doing is flexing dimensions, it's going to still do a high quality study. But again, when you start introducing things like simulation, this will interpolate between the studies it does run to predict what those other iterations would be. And then, like I mentioned before, you can always go in there and tell SOLIDWORKS, you know what, I really am interested in this iteration that you did not do. Please go ahead and calculate it. And then you can specify the results folder. Okay, either use the current document or set a user specified location. And with that, let's get back over to the slideshow. And for my next design study example, I have prepared for you a custom fish tank. Here you'll see I have essentially two fish tanks in one. In between the two halves, I have connector tubes. And my design requirements for these connector tubes are as follows. I want to base the location of these connector tubes upon the height of the tank divided by 3. In addition to that, I want to take into account the wall thickness of those connector tubes, which is going to be an 1/8 inch. And I'm going to want a clearance between these connector tubes. So I'm actually going to shift the position of these tubes based on double wall thickness. Therefore, when the tank gets taller, I want my connector tubes to shift location to accommodate the new size. In addition to their location, for the connector tube diameter, I want that to equal the first tube location. So as the tubes get spaced out, they will also get larger. In addition to this, on the outside corners of the tank, I want these chamfers, if you will, to be equal to 1/3 of the depth. So as my tank depth gets larger, I want these corners to get larger. And the two design studies that I'm going to run on this will be a 20-gallon study, so I can get 20 gallons for my volume of water. I'd also like to get a 50-gallon version of this tank from my design study. And with that, let's go into SOLIDWORKS to take a look at this. Okay, so back over here in SOLIDWORKS, I'm going to go ahead and open my fish tank volume. And a couple things here, you'll notice I've renamed some of the features in the tree. Now I'm going to go ahead and take a look at some of my dimensions. As you right click on the annotations folder, you can show the feature dimensions. And here you can see that I've renamed a few of them, but not all of them. First thing I may be interested in is the width. So to rename a dimension, I mentioned that you can click on it and access the information over here under primary value. But another handy way to name some of this stuff is to use a link value. And here I'm going to just call this width. Once I set a link value, if I needed to make this dimension equal to another dimension, I could then use link value and then from the drop down here assign those two dimensions to be equal. If I do that, no matter which one I change, it's going to update both of them. Okay, so link value will rename a dimension as you take a look at primary value here, but it also adds kind of like an equal relationship between those dimensions. Now the primary difference between this or an equation is with an equation I would say this is equal to that. In order to change this, I need to run over to the variable of that, modify that to influence this. So you have a parent-child relationship there. Okay, in the case of a link value, it doesn't matter where you're modifying the dimension. I can change it either from this dimension here to influence that, or I can change this to modify that. So big difference between a link value or an equation. Now, I do not necessarily want this one to be called width, so I'll unlink that and instead link this one to height. And then my last one here is going to be depth. Okay, and again, by adding link values, it adds that, or changes the name rather. Okay, but it also adds it to the equations folder. Underneath there, I can see the linked values for this model. This is also a tip if there are a few dimensions that you really care about that you want to call attention to. By adding a link value, they will show up in the equations folder in the tree. One of my first requirements I mentioned was the location of these tubes. Okay, so as I take a look at this tube here, I want to add a equation. And I want to say that that location is going to be equal to the height divided by 3. Now, I also want to take into account the wall thickness. So here I need to do some parentheses for order of operation. And I want to subtract my 1/4 inch. So now when I change the height of my tank, my tube will change position. So let's test that. If I change my height and then rebuild, my tube shifts. If I make that smaller, hit rebuild, the tube shifts. I want to do the same thing to the second one. So here, add equation, and I want that to be equal to the tank height divided by 3. Now, because this is the second one, I actually need to multiply it by 2. So I'll do times 2, and then I will add, in this case, because I want to shift it up, 1/4 inch. And when I hit rebuild here, you'll see that that second tube location responds. So all I'm doing is I'm adjusting the height, hitting rebuild, and watching the tube locations for both of them adjust. Okay, lastly, I want the tubes to get larger when my height changes. So here I'll double click on the tube diameter, add an equation for that, and I'm going to say that that is going to be equal to my tube location. Okay, once I do that, I hit rebuild, and that tube gets larger. Now to make this tube equal to that tube, I'm going to add an equation. The reason I'm not going to do link values here is a link values, you don't have a parent-child relationship. The fact that this is a child already of tube location means this cannot be a link value. A link value needs to be a top level or a parent. So here I'm going to do a simple equation and say that that's going to be equal to the first tube diameter. And with that, I'll go ahead and rebuild, and you can see that that updated. Now when I shift position down, that should update both the tube sizes and locations. And the last bit of intelligence that I want to add here is for the corner. I'm going to add an equation, and I want that corner to be 1/3 of the depth. So now when I adjust the depth, I want the corners to update. Now that I have the appropriate intelligence for my model, I have my connector tube's size and location based on the height. So when the height changes, then my connector tubes both move and get larger, as well as the corners, they will get larger or smaller based on the depth, maintaining that 1/3 ratio. Having all the intelligence that I need in this model, I'm going to go ahead into my design studies, and I've already set up a few parameters here. Okay, so for my height, it's linked to my height dimension. My depth is linked to my depth dimension, and the width is of course linked to my width dimension. So if I needed to add additional parameters, I could do that here, but I don't, so I'm going to go straight away into my design study, and now I can use these variables. I'll start with the width, and I want this to be arranged with a step, minimum of 8, maximum of 16, stepping every 4 inches. Next I'll control the height, going between 8 and 16. And this one is also arranged with step, and I'm going to do 2 inches. And finally I'm going to use my last parameter, the depth. Now with this one, I actually want to do discrete values. And the discrete values for this is going to be 8, 12, and 16. Now as I type each one of those in there, it's going to calculate the number of steps that is required to go through and check all this. Lastly, I'm going to set a goal. And for my goal, I'm going to add a sensor. And the sensor type that I want here is going to be mass property type, and it's going to be for the volume. And I want to check the volume of this body. And I want that volume to be 20 gallons, so I need that to be 4,620 cubic inches. And then I just click on Run. And now SOLIDWORKS will run through all those scenarios, adjusting the model. Let me move this out of the way so we can see that. I'm going to go ahead and jump ahead here. Okay, now you can see it ran through all my iterations, and for my volume, looks like the closest it gets is 4610 cubic inches. I wanted 4620. So that's pretty close to my 20 gallons. Now, if I had a range in mind that would be acceptable, I could go ahead and add a constraint. So here I'll add a sensor, another volume sensor. Okay, and I could tell SOLIDWORKS that I want to make sure that this volume is between a couple of numbers, maybe 4520 and 4720 cubic inches. When I run it this time, it'll do pass-fail based on my constraints. And now as we take a look at the results, you can see all the scenarios. And scenario 41 passed. It was larger than my 4620, but it was between 4520 and 4720. So it's within a range that I asked for, but this is my optimal result. Next, I'm going to go ahead and set this up for 50 gallons. So for this first one, I'll go ahead and rename my study. And I'll go ahead and duplicate this study. And this is going to be my 50 gallons. And for my variables, I'm going to change these up a little bit. My width is going to be between 12 and 20. Height between 12 and 20. Using the same steps on both. And my depth discrete values is going to be 12, 16, and 20. This time around, my goal for 50 gallons is going to be 11,550 cubic inches, and I may want to check between 10,500 and 12,500. Once I have that ready to go, again I just hit run. And so now, to meet my 50 gallons, 11,550, I'm pretty close here with the optimal. And as I take a look at some of my results, you can see that I had a few that were within my range. But again, I got fairly close by allowing SOLIDWORKS to pick the best option through optimization. Again, each one of these results, I can click to view it. And they are not separate configurations, but if I wanted to make configurations from them, for my 50 gallons here, I could go over to Configs, add a config, and then go over to my 20 gallons, toggle it so it'll refresh the dimensions, and then add a config. And with that, I'm going to go ahead and just view the model. So default, that I use for my design studies, and optimally 20 gallons and 50 gallons. And with that, we'll get back into the slideshow. Design study reporting. After we generate a design study, we can then ask SOLIDWORKS to generate a report for us. With standard SOLIDWORKS, we can define a history graph on a design variable, objective, or constraint. Now, if you happen to have SOLIDWORKS simulation, either through Premium or one of these simulation packages, you could then output a report in HTML or Word. And with that, we'll go into SOLIDWORKS to take a look at this. Okay, back over here in SOLIDWORKS, I'll pull up my 20-gallon study. And under the results, I'm going to go ahead and define a history graph. On the history graph, I can specify which design variable, objective, or constraint to watch or track. So at first I'm going to take a look at a design variable. And here I can see what the width does. Perhaps I'll take another look at maybe the constraint, the volume. So as it runs through the study, I can see how my volume changes with each scenario. The other type of graph that I can request is a trend graph. Now, in order to use a trend graph, you need to have first selected faster results, and this typically comes into play when you do a simulation design study where it has to calculate each iteration. And with fast results, it's not actually going to do all of the iterations or scenarios. It'll pick and choose, do a few of them, and then extrapolate the results. So a local trend graph would allow me to see those results and then show me what it's predicting the trend to be for the iterations it did not run. Now here, since I did a high quality study, I do not have that option right now. And then finally, if I add in simulation, and I actually do need to close this file and reopen it to load the simulation graphs. So let me close this file and then reopen it. Okay, now under here I have a new button. This is to generate a report. You can see that it has the simulation icon with it. And this will allow me to specify what type of report that I want. I can add additional items here. And I'm going to go ahead and publish my first one as an HTML. And here's my report. Tells me about the model, my study properties. Here it was doing high quality, the units, and my variables. The range was step, what they were, my constraints and goals, and then the results. So again, in order to get these simulation reports, you do need to add in simulation, close your file, reopen it, and then take another look at the design study in order for that to show up. And with that, we'll get back to the slideshow. And now that you've seen how to generate a design study, the next step is to figure out how to best utilize this automation of design intent. Well, there are two options here. We can generate multi-body parts. This is commonly referred to as a master model technique. Master model in the fact that I might generate a fairly complicated part but split it up into multiple pieces that is later joined in the process. One example might be a squirt gun, and the handle on it might be otherwise ergonomic. In order to put the internals of the squirt gun, I obviously need to make the handle in multiple pieces. Well, if I make the model in a single part due to the ergonomic nature of it, that is for modeling convenience. But at the same time, you can split that part into multiple parts or multiple pieces. This is just one of the many examples that you can come up with for this technique. Now, a couple of things that are unique about multi-body parts is the fact that we can use the feature called combine to perform Boolean operations, things like add and subtract. Some other features that might come in handy here, I can take one part and insert it into a new part or into an existing part. That would allow you to combine multiple parts into a single part, and then you could join them together, for example. Or you can take one of your bodies and save it out into a different part. One of the ones that's not used a whole lot is shell outward. This would be the ability to add a wall thickness on the outside of a part, commonly used in packaging. Or we could offset the outside surface of a body and thicken it, which also gives it a wall thickness, similar to shell outward. The other strategy here would be in-context assemblies. An in-context assembly would allow me to take advantage of all the multi-body part features and techniques, but have the following advantages as well. The ability to have virtual components, that is an assembly without any parts external to the assembly file, so I could save all of my parts in the assembly, or maybe the ability to lock references so they don't update, or break them once I have the model where I need it and I don't plan on changing it. And if it's really necessary to do Boolean operations like add or subtract, there are two features that are unique to in-context assembly design, and that is called join for add and cavity for subtract. Now, if you are going to employ the in-context assembly modeling method, which would be my preferred method here, you need to keep into account the status that's shown in the tree, the symbols that you see here. A feature preceded by the greater than symbol means that there are external references present. If you have that greater than symbol there with a question mark after it, it means that the assembly that contains the context or the other parts that this current part is related to would be currently closed. That is to say, the part may or may not be accurate, but to find out, you need to open the assembly where the context was generated or where that relationship exists. If you have this greater than symbol with an asterisk after it, it means that somebody has gone in there and locked the reference. That is to say that this part will not update until it is unlocked with the assembly open. Or finally, if you have this greater than symbol with an X after it, it means that someone has gone in there and permanently broken that reference. Once a reference is broken, it cannot be reattached. And with that, we'll go into SOLIDWORKS to take a look at some of this. Okay, over here in SOLIDWORKS, when I take a look at, let's say, the 20 gallon, some of the features here, maybe the shell outward. When I click on shell, I specify shell outward. I could tell SOLIDWORKS that I want an 1/8 inch wall, but I don't want it to shell those two faces. If I show the preview, you'll see kind of what it's going to do. And when I hit OK here, you can see that it's actually added material to the outside. So if I roll back here, you'll see there's my volume, and there's the part essentially larger than the volume. I'll do that again. Roll back. Shell outward. Basically grows a wall thickness on the outside of my part. And this works really well for design studies that are taking into account a water volume like we are here. If I wanted to take this and generate multiple parts from it, like maybe I wanted to separate each one of these pieces of glass, maybe I'd go ahead and take the top plane here. As you can see that that's where the bottom is joined. And I could go ahead and generate a split feature to cut the part. And then I have 3 different bodies. And now as I isolate one of these, I can show you what that piece of glass is going to look like. Okay, and then from here, with my 3 solid bodies, I could take one of those and insert it into a new part. And here I have my part. I can go ahead and give it a name, make a drawing for it. You'll note that it's based on the stock feature that's in context. By the way, that greater than symbol you can see is here. And if I list the references, I will be able to see where it's coming from, and it's currently in context. As I go back to the main part, I could go in there and split out each one of these glass panes, which I've already done in another file that I'm going to open up here in just a second. Another way to have approached this, aside from shelling outward, I'm going to go and delete these here, would be to go into our surfaces and drop in an offset surface, maybe offset at 0. Maybe I just want that panel. Okay, I can take that surface that I just made and generate a thicken. And one of the things you want to watch here is both direction and unchecking merge results. That way it does not join with the original. And you want to take a look at which side it's populating. I'm going to make sure to push it to the outside. Okay, so that would give me the front glass panel. And same deal, I could insert this into a new part if I needed to. Then the last thing here would be a Boolean operation. So for this, I'm going to go ahead and drop in one more feature, an extrusion. And basically I'm going to draw a circle up top here. And after I extrude it, I'm going to uncheck merge results. And through the combine feature, I can do an add to join bodies together. So if I join this one and that one, it would generate one new body. So let me isolate that body. If I was to do an add to the front plate, then it would look like this. Finally, if I was going to do a subtraction, subtract to pick the body you're subtracting from. So if I'm going to subtract from that, I can subtract that cylinder there. And as expected, it removed the material. I'm going to undo that. And finally, my last combine I'm going to show here is common volume. Okay, this would allow me to keep only what is interfering between those two. Okay, so a couple of different techniques here using combine with a multi-body part. I'm going to undo that as well. And now go ahead and open the assembly that I've prepared from this. Now before I do that, I'm going to go ahead and delete a couple of these items here. And I'm going to flip it back over to the default config. And zoom out. And then we're going to go and open that assembly. And in the assembly here, you can see that I have made multiple pieces from my primary tank volume. So here for the glass, as I open this part here, I've actually gone in there and added an extrusion. Here, actually I need to back up here, roll back. I added an extrusion, a surface extrude, to split each glass panel out. Okay, which I did here, which gave me 16 different pieces of glass. And on any one of them, you can isolate them to see what they look like. Okay. And what's good about this is it even has the bevel where these panels would otherwise be joined. Alright, and then I did a body delete to get rid of that surface that I no longer need. So I could insert each one of these into its own part, or I could save the bodies out and generate a file for each one of these. Now, since this is symmetrical, then half of these will be identical. Okay, so I'd probably just do one tube and then one side, and then just double my quantity when I go to order it. The next thing that I want to take a look at here is the fact that when I go to change the part, this will update. So I'm going to go ahead and show these by tiling them. And from here, when I take a look at my design study results, when I double click on a size, it updates my volume. Then when I click in my assembly, because everything's in context, it's going to update and adjust. So here you can see if I have a modular design, I can flip between my design study results and take a look at the actual result on my assembly, because I've modeled all of those other parts on the design study component, or my design intent part, in this case the water volume, and built the other pieces around it. So again, if you have modular design like this, go ahead and take advantage of these design studies and build an in-context assembly, also taking advantage of multi-body part design to make your job easier. And with that, we'll get back to the slideshow. Design studies for use in simulation. Earlier, when I was adding sensors, you may have noticed that you can add a sensor to track simulation data. This would allow you to set up a SOLIDWORKS simulation on a model in order to test multiple scenarios or iterations of a model to achieve a specific design goal. For example, you may want to optimize weight versus strength for your design. For a more in-depth discussion of design studies used in simulation, please check out our webcast archive site for the following webcast: SOLIDWORKS 2010 What's New Simulation. And as I click on this link here, our webcast archive site is webcasts.ddicad.com, and from here you can go to the SOLIDWORKS 2010 What's New, and then you will find SOLIDWORKS What's New Simulation. Best practices for design studies. Design studies should be used early on in the design cycle to help you find the initial design point or design parameters. It's also a great tool to help you when doing a modular design that may be subject to scaling. For example, my fish tank here, you saw that I was able to take a similar design at 20 gallons and quickly update it for a 50-gallon tank. Additionally, design studies is a great way to take models that maybe you've set up to use in DriveWorks in order to test all the criteria that you've built into DriveWorks, thus enabling you to catch any mistakes on a DriveWorks design before posting it and making it live. And with that, let's go into SOLIDWORKS to take a look at this. Okay, so to see design studies and simulation, I'm going to go ahead and open this model here. And for here, if you take a look at our sensors, you'll note that I have a stress sensor, a displacement, and factor of safety. So as I edit the sensor, you can see that I can specify a simulation data sensor type, so long as I have simulation added in. Then you can specify what you want that sensor to watch. And then, just like on our dimensions, I can have SOLIDWORKS alert me when this sensor, the data that it's watching, is greater than, less than, exactly, etc. Once it violates the given criteria, it will alert me like a SOLIDWORKS model error. Okay, but in regard to what we're doing here with design studies, if you take a look at my design study here, under the variables, you can see that I've set up a length, which is the location of this web here. The boss offset would be the location of this cylinder here. The large web thickness is over here. So when I click on these, you'll note that it's highlighting the dimension that they're talking about. Okay. And then the constraints, the things that I want to pay attention to or watch. Maybe I want the stress to be less than 150 megapascals. I want to monitor the displacement and monitor my factor of safety. My end-all goal here is I want to minimize the mass. So as I take a look at the results, you can see that I started with my initial design, and a couple of the iterations failed because the stress was over my given amount. These other ones have low stress, but they're much heavier than the optimal design. And the optimal design is, of course, one in which my stress is below my given value and the mass has been minimized. And again, when you go into your properties for your design study, if you do fastest results, then SOLIDWORKS will run through and test steps in between. It may not need to check every single iteration, and if you run into an iteration that was not calculated, you can always right-click on that iteration and have it run for you. This particular file, it did run through and do all the iterations, so I don't have to calculate it. But as shown before, if I need to save a configuration of any one of these, I can just go to add a configuration here. One other thing I might point out here is on your results view, these sliders, if you click and drag, SOLIDWORKS will vary those variables within the ranges that we set, and we can see visually that iteration. Now if I turn on my results, I can check out the stress, and as I click through each one of these, it's going to show me the stress plot for each one. And with that, let's get back into the slideshow to finish this out. Really quick, I just wanted to mention that DDI's community is as follows. You can follow us on Facebook at twitter.com/DDICAD. We have a Facebook fan page at bit.ly/DDIFacebook. Now, for those of you that have seen this slide before, our YouTube channel has changed. It's now youtube.com/DDICAD. And basically, if you haven't seen that yet, it's our video tech tips. You can find our podcast website at solidworksherd.com or join our microblog at herd.solidworksherd.com. Thank you for joining me on yet another DDI Productivity webcast. To see this and other webcasts, please find our website, webcasts.ddicad.com. I'm your host, Joseph Richter. Thank you.